Okay, now rate of reaction, we will continue with this same reaction, CO plus OH giving CO2 plus H. The rate of the forward reaction using the law of mass action is written using the concentration, which you have already seen as dCO by dt equal to K times CO power 1 and OH power 1, and this is law of mass action says that the reaction rate is proportional to the concentrations raised to appropriate powers. Here the stoichiometric coefficient itself for elementary reaction, but for global reaction it is not, we will see that later. The constant of proportionality is not a constant, but it is called rate coefficient K. So, the K is called rate coefficient, and it is not a constant, it varies strongly as a function of temperature. The rate coefficient varies very strongly. So, how to determine the rate coefficient? For elementary reactions, the rate coefficient K can be evaluated with some theoretical basis. So, kinetic theory can be used to have some estimation of K, but even then you should have some experimental data fit to correlate the value of K completely. So, because K is a strong function of temperature, we need some experimental data also to calculate this. So, what actually kinetic theory says is, to evaluate the value of K, what kinetic theory says. So, I have not gone into the entire derivation, but what it says I have just put it here. For successful occurrence of a chemical reaction, okay, Arrhenius and Van 't Hoff have defined the following conditions are to be satisfied. What are they? First of all, suitable molecules must collide. For example, here CO and OH should collide. Okay, collisions must be in proper orientation. So, CO and OH should collide such that the O atoms are going to be involved in the collision. O atoms should collide with each other, and the collisions must be energetic. So, proper orientation and energetic is we should have proper energy which is enough to break the bonds. Reactant bonds should be broken. So, these are the three important criteria for attaining a successful chemical reaction. Okay. So, suitable molecules must collide. So, CO colliding with say CO2 will not help, OH colliding with H2O will not help. However, CO and OH they collide properly. So, several molecules are present in this system, correct. So, only appropriate molecules should have collide with each other. So, CO and OH should collide. So, that means the concentrations of these two should be enough, so that like sufficient enough for the collision to occur in a proper way. Okay. So, if the concentration of one of this is very low, then this reaction will not trigger. So, the concentrations of CO and concentration and OH should be sufficient enough for triggering this reaction. Suitable molecules should be available at suitable levels of concentrations. Then proper orientation, O atoms should collide, that is very important. Similarly, energetic enough to break the bond. If they are not moving at so that means how energy comes for the moving molecules, temperature increases, energy will be higher. So, energy will increase T power 3 by 2. So, when you have sufficient temperature, the molecules will be energetic to collide with each other to break their bonds and form the new bonds, which are products. Okay, now what actually happens is, so here the energy of the reactant has to be increased to a level where they form what is called activated complex. So, let us see this is energy versus the extent of reaction. So, now this is reactant level, reactants are some energy level. Now, reaction cannot happen. So, some sources of ignition or some already available flame or hot environment etc. should be there for the reactants to increase its energy level to a value here, which is called activated complex. So, this is attained by initially by ignition, then the flame is formed or a hot environment prevails. The hot environment is sufficient enough for the incoming reactant to get heated up and its energy level increases from the value low value to a high value like this. once it attains the activated complex level, then the reactant disintegrate. Okay. Then they form products. Products go to a low energy level, correct? See, this is the product. So, these products are formed here, they are at low energy level, and this heat is released out, that is the heat of reaction that comes out as heat of combustion. Okay. So, this is the exothermic reaction. So, reactants are at higher energy level than products, but that is not sufficient for the reaction to occur. The reaction energy level should be increased, okay, to a value of that of the activated complex, so that you provide energy which is called E suffix A. To increase the reactant from the initial energy level to the activated complex energy level from which products are formed. Okay. So, now the energy of the reactant has to be increased to a level where they are in the form of activated complex, which can disintegrate to form the product subsequently. Now, collision between the reactant molecules should be strong enough for this to happen. Okay. That is what the environment should be hot enough and so on. Okay. Stronger collisions are possible by higher temperatures. Okay. So, now the difference between the energy level of the activated complex and the initial reactant is called the activation energy. So, this is the energy part of the equation, which is going to contribute to the rate coefficient. So, the rate coefficient has, see, for example, in the previous slide there are three things which we told. The energy part is the third one. Collisions must have enough energy level. So, the energy part comes for the third part. The first two, suitable molecules should collide. So, in a basket of several molecules, suitable molecules should collide. So, that some probability is there. Similarly, they should collide in proper orientation. Each collision may not happen at proper orientation. So, the first two actually are some probability dependent factors. Okay. Other factors like proper orientation or the collision between two molecules are probability oriented. So, probability that the collision will result in a reaction. That means that two proper molecules are going to collide or not. So, the other factors, the other two factors will contribute to a term called A in the rate coefficient equation. The rate coefficient, which is what we are going to now estimate. For that, the energy factor, which is the third one, is nothing but the activation energy, and the first two factors are probabilistic factors, which is going to be included in the term called A. Now, if you go to this, the activation energy and the term A, they are used to write the rate coefficient in what is called Arrhenius form. Arrhenius, say Arrhenius Van 't Hoff who told about these factors, no. So, Arrhenius form is nothing but when you write the reaction rate coefficient K, which is a strong function of temperature, as A times exponent of activation energy divided by RUT. So, you can see that if you write this in this form, the rate coefficient, then this form is called Arrhenius form. This Arrhenius form is very famous. So, there are two factors in this, one is the A and another one is EA, activation energy. So, now the exponent term is here. So, the dependence on temperature is very strong due to this term. Okay, now, since A appears before the exponent term, A is called pre-exponential factor. That is all. Just because it is just before the exponential term, it is called pre-exponential factor. And this A take into account of the probability whether the collision will occur between proper molecules or they will occur at proper orientation and they will be successful or not and so on. So, these are all like probability based things. That is what I told, even though kinetic theory helps us to attain some factors of this, experiments are going to help us in providing the final data to us. Okay. So, this is the way you write the Arrhenius form, pre-exponential factor A into exponent of activation energy minus of activation energy divided by RU, universal Gauss constant, into temperature in Kelvin. Now, if the temperature dependence, the range of temperature for which the rate coefficient is going to be calculated is wider, Then you add a third term like this, A T power m into exponent of minus EA by RUT. So, this is called 3 term, 3 factor Arrhenius equation, where the third factor is T power m, some additional contribution by temperature is added. Okay. So, for example, normally this the reaction rate is given in the molar basis, kilomole per meter cube second. So, for this reaction we can write dCO by dt is A into T power m into exponent of minus EA by RUT into concentration of CO raised power 1 and concentration of OH raised power 1. So, this is the way you write this. So, now this is nothing but the rate coefficient KT. Okay. So, rate coefficient is not a constant, it is a strong function of temperature here, and this is calculated by conducting lot of experiments, and you have to evaluate the value of A and EA for a set of species, and you have to fit curves to get these values. Okay. Now, forward reaction rate of this is given by this forward reaction. Similarly, you can also calculate the reverse reaction rate. Okay. But how we are going to do this? So, we conduct controlled experiments under isothermal conditions. So, we will maintain the combustion chamber at several temperatures, starting from say 1000 Kelvin or 800 Kelvin to say 1500 Kelvin or 2000 Kelvin and so on, and the concentrations of the reactants are recorded as a function of time, correct. So, we know the rate at which the concentration of CO reduces and concentration of OH reduces with time. Any one is enough for us basically. By getting the data at various temperatures, now you will conduct experiment at say 800, 900, so till say 2000 Kelvin, and once you get this data, you can plot the curve to extract the values of A and EA. So, this is the way the chemists report. This is a work which is done by chemists. They conduct lot of experiments like this and report the values of A and EA for several set of molecular level reactions. Even global reaction can also be done in it. So, for example, methane oxygen you put and monitor the concentration of methane as a function of temperature. That is what we are going to see later. Global reaction also can be done like this, reaction rate can be found by, or the rate coefficient can be determined for a global reaction also. But several the molecular reactions, several reactions have to be done, and chemists do this carefully to extract the values of E and A and EA and gives even the T power m, the m also they will give actually. So, by conducting several isothermal experiments and fitting the curves and this. However, the problem here is how accurate these data are. They are not very, the uncertainty when you do an experiment, okay, every time you do you will get some difference in the values, okay, that is called uncertainty. Okay. So, this uncertainty it should be within some limit, say 5% uncertainty. So, once you do the experiment one time and do it second time or third time etc., and take a mean and standard deviation. If the total variation or standard deviation is within 5% or something like that, then that is a good experiment. But it is not possible. See, its intention is to get good data, but it is not possible because of several conditions. So, the uncertainty involved in getting the rate coefficients are not so low, they are very high actually. Okay. So, what we do is either the forward or reaction rate coefficient is obtained from the experiments. Okay. Since the uncertainty involved in estimation of the reaction rate coefficient is quite high, it about say 40% also we can get, 40-50% also uncertainty we can get. So, we will not incur the same uncertainty while calculating the reverse reaction also. So, let us say I do the careful experiments in isothermal conditions and get the forward reaction rate coefficient A and EA value for that. Then I will not do the same thing for the reverse reaction. So, I will do something else for that. So, what I will do is I will find either the forward or reverse reaction rate and I will determine the other if I have measured the forward reaction rate, I will determine the reverse reaction rate using the thermodynamic procedure, which is much accurate. Okay, where I will use the, so what is the procedure we will see now. I will calculate the equilibrium constant and get the value of the reverse reaction rate. So that is what is the next step what we are going to do. Okay, so once you get the forward reaction rate from careful experiments, but it has higher uncertainty, I will not repeat that for determining the reverse reaction rate. For reverse reaction rate, I will use thermodynamic concepts. How? So now let us consider the same reaction, and let Kf be the forward reaction rate coefficient, it is a strong function of temperature. Similarly, Kr is the reverse reaction rate coefficient. At thermodynamic equilibrium, constant temperature and pressure, given pressure and temperature, equilibrium prevails. At that equilibrium, so reverse reaction rate and forward reaction rate are at the same rate. So Kf into concentration of CO power 1, concentration of OH power 1 will be equal to reverse rate Kr into concentration of CO2 power 1 and concentration of H power 1. These two are same. The rate at which the forward reaction takes place is same as the rate at which the reverse reaction will take place. Correct? So now the ratio of Kf by Kr, that is defined as the equilibrium constant K suffix C, capital K suffix C, and this is nothing but the ratio of the products of the concentration of the products divided by the product of the concentration of the reactants. So when you write the reaction like this, the reactants are CO and OH, products are CO2 and H. So this is the concentration of the products sum multiplied together. Similarly, this is the concentration of reactants multiplied, and that ratio of the products to the reactants, that will be concentration based equilibrium constant. So K, the suffix C is nothing but the concentration based equilibrium constant. So that is nothing but the ratio of the forward reaction coefficient, rate coefficient divided by the reverse reaction rate coefficient. So Kc is the equilibrium constant written in terms of concentrations of the products and reactants. This can be related to the Kp value. Kp we have already seen, partial pressure based equilibrium constant, which is evaluated using standard Gibbs function change at a given temperature. Correct? So Kp we know we can evaluate for any reaction like this, we can evaluate this as using, so for this reaction actually partial pressure base you can write. So PCO2 by P, then PH by P, P is the total pressure divided by PCO by P into POH by P. Okay. So partial pressure base you can write Kp, and this Kp can be calculated as a function of temperature alone by using standard Gibbs function change, which we have seen already in the equilibrium. Once you know that, if you connect Kp and Kc, then I can evaluate one of this, Kf by Kr equal to Kc. So I can evaluate one of that. Okay. So how will you connect Kp and Kc? So consider a general reaction. Capital A, capital B are the species, and small a and small b are the stoichiometric coefficients. Similarly, capital C and capital D are the species, product species, and small c and d are the stoichiometric coefficients. So A plus A times capital A plus B times capital B giving C times capital C plus D times capital D is the general elementary reaction I consider. And for this Kf by K, I can have backward reaction or reverse reaction, Kb is equal to Kr. Okay, anything I can write, that is nothing but Kc, concentration base I am writing. So here concentration rise to the appropriate power. So concentration of C power small c, concentration of D power small d, and so on, divided by the reactants, A power small a, concentration of B power small b. Now this equation is called Guldberg-Vaghese law of chemical equilibrium, which is written in the concentration base. So rate of the forward reaction divided by the rate of the backward or the reverse reaction is nothing but the equilibrium constant based on concentrations Kc. Okay, now the relation between Kp and Kc, now try to write the partial pressures here. So, now concentration, what is concentration? P V equal to N RU times T. What is concentration? P N by V. So, P equal to N by V into RUT, this is the concentration C. So, P equal to C RUT. So, now concentration will be equal to P by RU times T, that is the concentration. So, concentration of any species, say C, is nothing but the partial pressure of the C divided by RUT power the stoichiometric coefficient C. Similarly, for D and A and B, write this. Now, you also have this definition, partial pressure based Kp, partial pressure to the power of, again this is actually to the power of 1 you have to put, no. So, because the stoichiometric coefficients, okay. So, now you can equate this. So, that Kc will be equal to Kp times P power 0 divided by RUT. So, here actually see this will be P naught, this will be P naught, okay. So, now you can write this Kp, P power, this is atmospheric pressure, so 1 atmosphere divided by RUT to power of delta Nr, which is the sum of the stoichiometric coefficient of the products minus sum of the stoichiometric coefficient of the reactants. So, that so for a bimolecular reaction, for example, if A, B, C, D are having values of 1 each, then delta Nr will be 0, then in for that case, okay, Kp will be equal to Kc. So, once you know Kp, you can calculate Kc. Kp can be calculated using Gibbs energy change, function change at a particular temperature. Then you can use that to calculate Kp, calculate Kc. Once Kc is known, one of this is measured, Kf or Kb, and one of them is calculated using Kc, which is much accurate than the measurement itself. The next topic is net reaction rates. So, when you have several reactions like this, okay, H2 plus O2 reversibly giving HO2 plus H, you can see that these are some of the reactions which is participating in the hydrogen oxidation. So, this is a mechanism. I am just selecting 4 elementary reversible reactions in this, and to demonstrate how you calculate the net reaction rate out of these considering these 4 reactions. Okay. Now, in each of the reaction there is a forward rate coefficient Kf. See, for example, the first reaction, reaction 1, Kf suffix 1 will be the forward reaction rate, and the Kr1, K suffix R1 will be the reverse reaction rate of the equation 1. So, in general, Kfi will be the forward reaction rate of the ith reaction, 1, 2, 3, 4, I can be 1, 2 or 3 or 4. Similarly, Kri is the reverse rate coefficient of the ith reaction. So, now you know this. Okay. Now, net rate of production or consumption, when there is a species in the reactant side, it will consume in the forward reaction, but it will produce in the reverse reaction, correct. So, for example, if you take O2 here, O2 is consumed in the forward reaction of R1, forward reaction of R1 is consumed. Similarly, it is consumed in the forward reaction of reaction 2, R2. It is consumed in the forward reaction of R4. So, in 3 reactions O2 is consumed. Okay, where it is formed? In the reverse reaction of R1 it is formed, reverse reaction of R2 it is formed, reverse reaction of here R4 it is formed. So, the net reaction rate will be if you add the reactions through which it is formed minus the reactions through which it is consumed, then you will get the net reaction rate, okay, the net rate of production or consumption of the species you will get. So, you have to consider all the reactions in which the species is participating and see whether it is consumed or whether it is produced through a forward or reverse reaction suitably. Then you have to add these production terms and subtract to that the sum of the consumption terms. So, the net rate of production of production or consumption of O2 is written like this. So, as I told you, the reverse reaction of 1, 2 and 4 O2 is formed. So, add them. The reaction rate of 1, reverse reaction rate of 1 is the rate coefficient, reverse rate coefficient into the HO2 and H are the reactants which is forming O2. Similarly, OH and O forms O2, HO2 and M forms O2. So, appropriately you add them. Then subtract that to the consumption of the O2. In the forward reaction of 1, 2 and 4, O2 is consumed, and the reaction rate corresponding to that is Kf1 into H2 plus O2 consuming O2, H plus O2 consuming O2, H plus O2 plus M consuming O2. So, here we can, so the net reaction rate will be the chemical equation which will produce O2 should be added, which will consume O2 should be subtracted, and this is the net rate of production or consumption. We do not know that it is positive or negative, correct. So, production or consumption of O2 is given like this. Similarly, for H atom I can write like this. So, you can see this. So, this is only for 4, but actually we will have several number of equations, reactions like this, and we have to suitably know where the species is present, in what all reaction species is going to be present, particular species, and try to calculate. So, I need this term basically and this term to be substituted in the species conservation equation. So, the species conservation, O2 can be transported into the combustion chamber, and it is going to be consumed. For example, net rate is negative, it is going to be consumed, then some of that which is not consumed will come out, or if it is fully consumed it will not come out at all. So, based upon this, the conservation of O2 if you want to do, I need the net rate of production or consumption of O2, that is got by this. Similarly, for every species involved in the multi-component mixture or the chemical kinetic mechanism, we have to do this. So, this is very important to calculate from the mechanism. Okay, considering a set of equations, we have to find the number of species which are there in the equation mechanism, reaction mechanism, and for each of this, okay, except one. So, if there are n species, okay, we have to find the net reaction reaction rate, okay, this is production rate or consumption rate for n minus 1 species. One species we can find basically, we need not even find, because that may be an inert species and so on. Okay. So, this is what is important to find. So, you have to accommodate all the reactions which is important, like in which the species is participating, and suitably give the positive sign for the reaction which is producing that particular species, a negative sign for the reaction which is consuming that species, and add them. Okay. Now, so after knowing the rate at which reactions take place, we need to know the time. So, that is what the first we started with. So, what is the time required for the reaction to complete, and whether that is enough for the within the dimension of the combustion chamber will the reaction complete. So, some time scale I want, chemical time. How will you calculate the chemical time? Okay. So, just I will illustrate with two types of reactions. So, the elementary reactions let us consider here. So, unimolecular reaction, A giving B. Okay. So, reaction rate is the rate at which the concentration of A changes with time. Actually, A is reactant, so I put a minus here, minus Ku into A, concentration of A, because concentration of A is the, so the law of mass action, so the only reactant is A. So, put this power 1. Okay. So, now I separate the variable d concentration of A by concentration of A will be equal to minus Ku into dt, integrate this at a given temperature to get the concentration of A as a function of time will be equal to concentration of A suffix 0, which is the initial concentration of A. When I put the start the reaction time t equal to 0, what is the concentration of A? That is A suffix 0, concentration of A suffix 0 into exponent of minus K suffix u. So, K, this is unimolecular rate constant. So, unimolecular reaction. So, it is K suffix u is unimolecular rate constant. Again, Arrhenius form or 3 terms can be used to evaluate Ku. So, that is different. So, this is a function of temperature, that is what you have to understand here. So, now, so when I want to find the time, what is the time I will normally find is, let the time taken, the characteristic time I am talking about, time taken to for A to reduce to 1 by E of the initial concentration. That time, let us say, is tau. So, tau is the time when the concentration of A will fall from its initial concentration of A suffix 0 to 1 by E of that value, the initial concentration value. So, that will be in the unimolecular reaction, it will be 1 by Ku. So, based on the temperature alone, it will change. So, based on temperature, Ku will change. Temperature is higher, Ku will be higher, so time taken will be lower. So, we will have some idea of how the reaction chemical time will change. So, based upon this time I will, so why I am taking 1 by E, why I am not taking A naught to 0, because normally asymptotically it will reduce, it will take longer time for it to to reach a value of 0. So, but if you consider this, this is the time we should plan for the reaction to be completed, but this is very low time based upon temperature. Basically, if the temperature is higher enough, then tau will be low, because Ku will be high at higher temperatures. Okay. So, the characteristic chemical time of a unimolecular reaction depends only on the temperature and it is independent of the initial concentration. Okay, now you take bimolecular reactions are mostly used. Okay, so we are only talking about these two. So, bimolecular reactions, I told 90-95% of the reactions, elementary reactions are bimolecular in nature. So, how to write this reaction rate for this? Take any one of the reactants, d concentration of A by dt will be equal to minus Kb, because it's, I know it's consumption, A power 1, concentration of A power 1 and concentration of B power 1. So, this we know, law of mass action, we write this. Now, if the reaction, if this reaction is predominant, not affected by other reactions, okay, then we can say that, see, for example, why I am saying this, because see B, if the set of reactions are there, this reaction is predominant in that set. That means the major consumption of A or B will occur only due to this reaction. If that is so, okay, if major consumption of A or B is going to occur only by this reaction, okay, other reactions are not majorly going to affect this reaction, then the change in the concentration of A, okay, let us say it is X, it is nothing but initial concentration minus the concentration at a particular time instant t, that is A. So, A suffix 0 minus A, that will be same as the difference in the initial concentration of B to the concentration of B at a particular time, same time. Okay. So, now this equation can be used to write the concentration of B at any time as concentration of A at that particular time plus the initial concentration of B minus initial concentration of A. Now, substitute this in this equation for any time, at any time t, you substitute this and you can write at any time t, the concentration of A divided by the concentration of B will be equal to the initial concentration of A divided by the initial concentration of B times exponent of this minus of B naught minus A naught times the molecular rate coefficient Kb into T. So, now again the time required to reduce the concentration of A from initial to the 1 by E of the initial value, that if you take as tau, then tau is evaluated like this. Okay, now here the denominator d is B naught minus A naught into Kb. So, this is the equation. So, you can just work it out, it is very simple separation and integration. So, you just work it out, then you get this value. Now, one important factor here is, if the concentration of the one of the reactant, say B naught is very high than A naught, okay, out of the two A and B, the concentration of one may be very high than when compared to the other. In that case, then we can write the tau as this. We are estimating the characteristic time. Characteristic time is the typical time of a reaction to complete. So, that time will be dependent on the higher concentration species, reactant species. So, Kb is also present in the denominator, B naught also is present. So, if Kb is higher, this is because at high temperatures Kb if it is higher, then the tau will reduce. Similarly, the initial concentration depends on the tau has come here. If the initial concentration is higher, then the time taken is low. If this reduces, B naught reduces, then the time will be higher. So, chemical time, some characteristic chemical time can be calculated using this analysis.